In this video, we'll talk about how to write chemical formulas for binary compounds. You'll recall that binary means that there are only two different elements within the compound. So you've already learned that if you have the formula BaCl2, you can name that and call it barium chloride. The question is, could you have gone the other way? For example, would you have known that there were two chloride ions going with each single barium ion? Writing the formulas for covalent compounds is pretty easy if you already know the meaning of the prefixes. For example, if you wanted to write the formula for diboron trioxide, you would just notice the di in front of the boron, which would mean there are two borons, and the tri in front of the oxide, which means there are three oxygens. Let's say you're doing silicon dioxide. In this case, you'll notice that there's no prefix in front of the silicon. That implies that the prefix would be mono, and therefore there's only one silicon atom. The di in oxygen, of course, means there are two of them, so we have SiO2. Now we're going to talk about naming ionic compounds. I'll move the title over here to give me more room to work. Let's try writing the formula for the compound sodium chloride. We start off with a sodium atom, which has one valence electron. So what it would like to do is to lose that electron and become a positive sodium ion. Then we have chlorine, which has 7 valence electrons. It would really like to gain one electron, becoming a negative chloride ion. You should recall that there's actually a +1 charge on all of the alkali metals, including sodium. So I put +1 at the top of its column. And there's always going to be a -1 charge on the halogens, of which chlorine is a member, so I'm putting a -1 on top of its column. Here's the most important thing. Every ionic compound, in order to be stable, has to be electrically neutral, and that means it's going to have equal numbers of positive and negative charges. In this case, the sodium atom has a positive charge and the chlorine has a negative charge. So it works out that if you have one of each of them, you add those two charges and you come to 0, meaning you have a neutral compound. But we're not going to write it this way. We're going to leave the charges off and just write it as NaCl. Note that if there's only one atom of the element, we don't write a subscript. Here's a compound we've seen before, magnesium chloride. We know from the name that it's going to include both magnesium and chlorine, so I can just write those symbols. Now, the magnesium atom we know is going to have a +2 charge because it's an alkaline earth metal, has 2 valence electrons. The chlorine we already know is going to have a -1 charge. It's a halogen, it's got 7 outer electrons, it wants to gain 1. Now, again, the whole point is this has to be electrically neutral, equal numbers of positive and negative charges. In order to make that work, we would actually need 2 of the negative chlorine ions, chloride ions, to go with 1 of the magnesium ions that has a +2 charge. The reason is that the +2 charge and 2 of the -1 charges will give us a total charge of 0. So therefore we're going to write the formula this way with MgCl2. Let's try combining potassium and sulfur to produce potassium sulfide. We know that the potassium ion will have a +1 charge. The sulfur, being in the oxygen group, will have a -2 charge. In this case, that means we'll need 2 of the potassium ions, both +1 charge, to go with the -2 charged sulfur atom, or sulfide ion. That means that our formula will be K2S1, or we leave the 1 off, so it's just K2S. And of course, anything in the oxygen column, the oxygen group, will have a -2 charge. Let's try magnesium oxide. Now in this case, the magnesium again will have a +2 charge and the oxygen will have a -2 charge. In order to become electrically neutral, all we need is one of each. A -2 and a +2 add up to 0. So we'll just write the formula as MgO. Something we could have done with the other examples as well is to use the fact that all of the elements in a group have the same charge on them to write other compounds. For example, we could take calcium in the same group with magnesium and sulfur in the same group with oxygen and write the formula for calcium sulfide, 1 and 1, just like the magnesium oxide. We could also try taking strontium with, say, sulfur again, and that would be SRS. And we can do a little mix and matching by writing magnesium sulfide. Let's try one that's a little trickier, aluminum oxide. Now we know that the aluminum, being in the boron group, is going to have a +3 charge on it. So I'll go ahead and write that. The oxygen, we know, has a -2 charge on it. The question is, how many of each do we need so that we end up with equal numbers of positive and negative charges? It turns out that if you have 2 aluminum ions, 2 times +3, that gives a total charge of +6. If we take 3 of the oxide ions at -2 each, that's 3 times -2, that gives us -6. Adding the positives and the negatives, we come up with a neutral compound, 0, which is exactly what we want. So we ended up with 2 aluminums and 3 oxygens, so we write aluminum oxide as Al2O3. Compounds made from elements in the same group will have the same pattern. So we could write, for example, gallium sulfide, or we could write indium selenide, or even aluminum selenide. What if we want to write something like iron oxide? The problem with this is there's an ambiguity. We don't really know what the oxidation state of the iron could be. It might be +2, it might be +3. This is where the Roman numerals come in. Instead of writing iron oxide this way, instead we would see the compound written as iron 2 oxide, or perhaps as iron 3 oxide. The way this works is that the Roman numeral 2 means that the iron is going to be in the +2 oxidation state, means it lost 2 electrons. In the same way, the iron 3, the Roman numeral 3, means that the iron is in the +3 oxidation state, lost 3 electrons. Now the oxygen still has a -2 charge, so in the case of iron 2 oxide, you have the +2 and the -2 and go together to make 1 and 1 iron oxide FeO. In the other one, we have the same -2 charge on oxygen, and it works out that the neutral balance comes with Fe2O3. Another example like this. Let's compare tin 2 oxide with tin 4 oxide. In the 2-tin oxide, the tin has a +2 charge. The oxygen with its -2, put them together 1 and 1, and we have the compound tin 2 oxide SNO. In the other one, we have tin with a +4 charge and the oxygen with a -2. Put them together, and we'll need a 2-to-1 ratio, 1 tin to 2 oxygens, and that's SNO2, tin 4 oxide. It's important to remember that writing chemical formulas is really all about making sure we have balanced charges. But is there a trick involved also? If we write the sodium chlorine with their charges, we can see that I can just sort of reverse the numbers and get 1 and 1 and write the correct formula, sodium chloride, NaCl. If I try this with sodium oxide, we have a 1 and a 2, -2, reverse the numbers, and we get Na2O for sodium oxide. That's correct. We could try even aluminum oxide with the +3 for aluminum, -2 for the oxygen, reverse the numbers, and we get Al2O3. This always works as long as we watch out for this kind of situation, where the magnesium has a +2 and the oxygen a -2. You might think we should write this as Mg2O2, But no, you know we have to actually reduce those subscripts and get MgO. If you want to know why this trick works, you'll have to figure that out for yourself. And now, armed with a conceptual understanding, a trick to use, and a lot of practice, you're going to be a master at chemical formula writing.